let's solve the problem of the electric field of an infinitely big sheet charge. Well, here is the question. We have a positively charged sheet with a uniform charge distribution, sigma. The problem tells us to find the magnitude of the electric field vector at a distance d from the sheet. Hint. So there's a hint in the question. Use a cylinder for a Gaussian surface. With the hint. How can we do this problem? Well, since the hint also tells us to use a Gaussian surface, we're going to use Gauss's law to calculate this electric field. But we have to imagine a few things first. What? So this is my sheet charge. That's what it looks like. Guys, usually when we say sheet charge, you would kind of ignore this thickness. You would treat it as a piece of paper, okay, some very thin sheet. And the charges are located not inside the volume, but they're located on the surface. Okay, so this may as well be a conducting sheet like an aluminum foil, okay? The charges would be on the surface. Hence, we are already giving you a charge distribution that is an areal charge distribution, not a volume charge distribution. So we have the sigma here. For us to be able to use Gauss's law correctly, we have to be able to imagine the electric field lines in 3 dimensions. When we say an infinitely big sheet charge, it would be like everywhere in this sheet charge is like the center of the sheet charge. So let's imagine the center, what would happen at the center of the sheet charge, right? If I wanted to calculate this using a DQ integration method, for example, I could pick a DQ somewhere and draw its electric field line, which would have components along this axis towards the right and another component perpendicular to it that is on the plane of this sheet. You can always find a symmetric DQ to cancel off that component that is parallel to the sheet, the plane of the sheet, or perpendicular to the component that is towards the right. And those components would cancel each other out, and you would end up with an electric field towards the right. Since everywhere on the sheet charge is like the center of the sheet, that's what kind of an electric field you have. You would have the components parallel to the plane of the sheet vanish, and then all you would have left is the electric field components that are perpendicular to the surface of the sheet. So your E field lines would be like this: perpendicular to the surface of the sheet and away from the surface if plus, towards the surface if negative. So this is what it looks like. Wonderful, beautiful. So all plus charges lined up, their electric field lines point away from the sheet, perpendicular to the surface of the sheet. That's the cross-sectional view. So what kind of a surface can I choose to calculate these E field lines, right? All right, the hint already tells us to pick a cylinder, but you can put a cylinder in various ways. But remember our criteria for Gauss's law. In Gauss's law, we calculate the electric flux, right? So to calculate electric flux beautifully, to get it out of that integration E.dA, we need an E that is going to be uniform. So only way I can do this is if I put a cylinder, all right, cutting through my sheet, extending both ways, so that the flat surface of the cylinder is parallel to my sheet, the plane of the sheet. I could also do this with a rectangular prism cutting through my sheet. Why? Because guys, on the surface of the cylinder that is parallel to the plane of the sheet, right, my E field lines will be coming towards the surface, perpendicular to the surface, right? Hence, there will be a 0 degree between the area vector and the E field vector. Wonderful. And on this surface that is parallel to the plane of the sheet, since it's parallel to the plane of the sheet, these points on the surface are the same distance to the sheet charge. Hence, the E field numbers, the E field vectors will have the same number, the same magnitude on this flat surface of the cylinder. Okay? Let's see with a picture. What would happen then on the round side of the cylinder? Would we get the same thing? Well, On the round side of the cylinder, your area vectors are radially out, yes, but the E field vectors are sweeping the surface. They're sweeping the surface. See, they're all parallel to the round side of the cylinder. They're all parallel to the round side of the cylinder. So the angles here between DAs and E's is the same number for all of these selections, and it's 90 degrees. So this is a radially outward vector. This is a vector on the plane of the, or not, this is not a plane, but this vector is on the surface of the round side, and the area vector is perpendicular to the surface at this location. So 90-degree angle here. This E field vector is parallel to the surface at this location. Area vector is perpendicular to the surface. So wherever you are, you have a 90-degree angle on the side between E and DA. Hence, you are going to get a cosine 90 in your flux calculation, which will give you a zero flux on the round side. And these E field vectors will have different magnitudes. It's fine because they are different distances to the sheet charge. But it won't even matter because you have a zero integral anyway. Okay, so this cylinder put this way is a beautiful choice for us to calculate the E fields at a distance from the sheet charge. So how do we pick this cylinder? Let's look at a cross-sectional view. Let's get a picture on this cross-sectional plane. So this is my sheet charge plus charges. E field lines are perpendicular to the surface and away towards both directions. All right. This is my cylinder cutting through the sheet. Okay, that's my Gaussian cylinder. Guys, the trick is this. Since E fields may change with distance, to make sure that my E field is the same, I'm trying to calculate E field at a distance d from the sheet charge. My cylinder extends towards both directions a distance d. Okay, towards both directions, my cylinder extends a distance d. So then, these E fields are the same number as this E fields, as the E fields on this surface. They're the same number. Wonderful. So I can use a uniform E in my calculations because all of these points on the surface, they're the same distance to the charge, so they will be uniform. Also, the E fields are going to be towards the right, coming perpendicular to the surface, this circular surface, and then the area vector is also perpendicular to the surface. So what I see here is that all of my E fields are going to be parallel to my DAs on both the bases of the cylinder. Both the bases, I have E fields parallel to DAs. So that makes my flux calculation very easy. And I just argued that all the points on these bases, they're the same distance to the charge, so E field is uniform. Hence, my flux calculation doesn't need an integration. There's a 0-degree angle between E and DA. So the flux is just E times area. That's it. On both the bases. Okay, base 1 and base 2. It's both E times A because they have the same area. Okay, wonderful. Some people usually ask me this question when I'm teaching this in class. Hey, the E fields here are towards the opposite direction, so wouldn't you get a minus E times A? No, you don't, because here your area vector is also towards the left. E field is towards the left, hence the angle in between is 0 degrees. So guys, let's put this in a full total flux calculation. Let's calculate the total flux. So the total flux is on the bases, base 1 and base 2, plus the flux on the round side. And we just argued that the round side would have 0 flux because of the angle between E's and DA's being 90 degrees. So base 1 will have a flux of E times A. Base 2 will also have a flux of E times A. So the total flux is 2 E times A. A is the area of the circle. We can assign it a radius or we can just use it as A. Both are correct. That brings us to the final calculation of charge enclosed, because our Gauss's law has a Q in inside. Total flux equals Q in over epsilon 0. So let's get to calculation of Q in. Charge inside my Gaussian cylinder is this orange region that I highlighted. Let me also highlight it here. It's this orange region that the cylinder cuts through. And cylinder cuts through a region that is like a circle, the same area as the base of the cylinder. So if this is A, if I call this area to be A, I'm enclosing an area that is also A. So how do I calculate charge that corresponds to this area? Well, I have defined a surface charge distribution sigma, which is Q over A. That's the definition of sigma. So if I multiply my charge distribution, surface charge distribution sigma with the area, then I get a Q in, the charge that I'm enclosing here. So sigma times A is my Q in. Let's plug that in the equation. 2 times E times A, or A times E, equals Q in over epsilon 0, which is sigma times A over epsilon 0. That gives us an E. A's cancel. That only depends on sigma. E equals sigma over 2 epsilon 0, independent of the distance d. So we get a constant electric field near an infinite sheet charge that is independent of distance. It's uniform across the sheet and, near the sheet or away. You have the same number, sigma over 2 epsilon 0. Okay, electric field of a sheet charge, a big sheet charge, with surface charge distribution sigma. That's it. That is the answer, you guys. So I will tie this to another question that is also in the lecture notes that we haven't covered. What is the electric field created by two charged plates that both have a surface charge distribution of 1 microcoulombs per meter squared? And in this picture, you see the plates. They are separated by a distance d. One is positively charged and the other one is negatively charged. So what do you do to calculate the electric field between these two plates with the same sigma, same charge, surface charge distribution? Well, guys, we have to think of vectors here and vector addition, right? This charge plate is going to create an E field that is towards the right. Its magnitude we just calculated using Gauss's law to be sigma over 2 epsilon 0, right? But then I have this negatively charged plate, which also creates an electric field that is perpendicular to its surface. So since it's a negative charge, this guy was creating E field lines away from itself. This negatively charged plate is going to create fields that are towards itself. So the electric field created by the negatively charged plate is also towards the right. Also follows the same arrow. So actually here in the region between the plates, I have the same electric field vector for the plus and minus charges. Hence, I have an electric field in magnitude that is 2 times sigma over 2 epsilon 0. One from positive, one from negatively charged plate. Hence, we have an electric field that is, twos will cancel each other off, right? 1 microcoulomb per meter squared, which is 1 times 10 to minus 6 coulomb per meter squared, divided by 8 times 8, 5, 10 to minus 2 for 10 to minus 12 for the electrical permittivity of air, which gives us a number that is 11.2 times 10 to 4 newtons per coulomb for the electric field between these plates. Wonderful. Well, I have another question at hand for you guys. Also in the lecture notes that we haven't covered. So here is a positive charge that is released from the first plate. Here, its magnitude is 2e. So 2e of charge is released from the first plate. What happens to this charge? What is the work done by this electric field to carry the charge across the plates? How do we do it? Well, we have to think of the forces involved, right? Because work can be calculated by multiplying the force by distance. It's actually a dot product of force and distance, or displacement, in this case delta R, displacement, right? So let's use this equation to carry out the calculation for work done. Force on this charge will be F equals QE, Q times the magnitude of this charge times the electric field in between, right? Times the distance it will travel. This charge will be carried across the plates, so it's going to travel a distance of 5 centimeters. Let's just call it D for the time being. So work equals Q times E times D. Work done by the electric field to carry this charge across the plates. Hence, we can actually calculate a number, but we have to make sure that we write the value for E, which is 1.6 times 10 to minus 19. We also have to make sure that we convert this 5 centimeters to meters. So there is the conversion, 0.05 meters, and that was our electric field. So we get 1.8 times 10 to minus 15 joules of work that the electric field does to carry this charge across. Well, not big of an energy change it is. Wonderful. So guys, the electric field did this much work on this charge to carry it across, which means this particle's potential energy changed minus this much, minus 1.8 times 10 to minus 15 joules. The total potential energy change per unit charge, guys, which is this number, minus 1.8 times 10 to minus 15 divided by 2 times 1.6 10 to minus 19, 2e. Then, guys, this is the energy change, potential energy change of this charge between the plates, okay? This means this much of its potential energy turned into kinetic energy, accelerating this particle towards the negatively charged plate. So we can actually indeed calculate the kinetic energy of this particle when it hit the negative plate, but that's not our goal. So this total potential energy change per unit charge, guys, this is called the potential difference, right? It's the potential energy change per unit charge, or work done, negative work done on unit charge by the electric field. It's called the potential difference. We have covered electric potential in class. So remember, it was energy per unit charge. That was the units. So here the result of this calculation is minus 5.6 kilonewtons meter per coulomb, right? So it's minus 5.6 kilovolts in this case of potential difference exists between these two plates. So joules per coulomb is the units for voltage potential difference, and it's actually called volts. So delta V then means potential difference between 2 points. So in this case, if a particle left this plate at location A and reached this plate at location B, its energy difference between points A and B, potential energy difference, is the minus work done by the electric field, okay? And what this particle is actually doing is that it's going from a high potential energy point to a low potential energy point. Just like a pen falls from a height towards the ground, it loses its potential energy, which then turns into kinetic energy. Same thing happens here. This particle goes from high potential energy towards low potential energy, gaining kinetic energy. So this difference goes into the kinetic energy of the particle. But sometimes you don't want to just observe or explain energy quantities on a particle. Sometimes you want to talk in general. That's why you have the electric potential for it. So this location A is at a high electric potential, and this location B is at a low electric potential. So the potential difference between the 2 points is a number, being its energy per unit charge. It's the energy difference per unit charge. A unit charge would experience going from point A to point B. That's what potential difference is. All right. And this energy that it has, the potential energy, is called the electrostatic potential energy. U equals Q delta V, or delta U equals Q delta V is a more accurate expression. All right. Actually, this can help us derive the formula for potential energy difference between 2 points. It comes from the work expression. So you replace F dot dr in the work expression by F over Q, F per unit charge dot dr. Then you get the electric potential equals minus E dot dr. So that's where this expression actually comes from. It comes from the definition of work. All right. Thank you guys for listening, and I'll see you at the next video.